Hi, this is Juan from JuanTutors.com. Welcome to my totally free office hours. Today we're working on the August 2016 New York Algebra 1 Common Core Regents exam, problem number 17. If you want to access any of these exams, go online, nysedregents.org. Click on the appropriate tabs, and all the tests are available to you for free. So here's the problem. The table below shows the temperature, T of M, of a cup of hot chocolate that is allowed to chill over several minutes, M. There's a time and a temperature. Which expression, I do look at the data. Time and temperature is 02468, and the temperature is 150, 108, 78, 56, 41. And I don't process the data much more than that during the first read of the problem. Which expression best fits the data for T of M? 150 times 0.85 to the M, 150 times 1.15 to the M, 150 times 0.85 to the M minus 1. Or 150 times 1.15 to the M minus 1. Okay, so now I process the data a little bit. I notice that the temperature is going down over time. It's cooling as expected. So I notice also that all the exponents are positive multiple of M, with maybe a minus 1 here. But M is positive. So M minus 1 and M, they're all increasing. The exponents are all increasing. So for the function to be decreasing, the base has to be a number between 0 and 1. So that immediately eliminates choice 2 and choice 4. So even if you don't know how to do this problem, even how to use the calculator to do this problem, you already have a 50-50 chance of getting this question right. So how to do this problem? We can evaluate the function. That's one of the possibilities. Okay. There's also the possibility of the calculator you can type in these numbers into the calculator and let it create a model for you, an exponential model for you, and the data is going to fit one of these choices very well. But let's say we wanted to test choice 1. 150 times 0.85 to the 0. So if M equals 0, we're going to test this situation, equals 150 times 0.85 to the 0. Any number to the 0th power is equal to 1. So 150 times 1 is 150. Which fits the first problem nicely. 150, let's test this one over here. To the times 0.85 to the 1 is equal to 150 times 0.85, I'm sorry, to the 2, What am I doing? Sorry, I'm not, that was just a quick error. Let's plug this into the calculator. 150 times 0.85 to the power of 2, and we get 108.375, which fits the data very nicely. So 108.375. So it seems to be that choice 1 is the answer. I'm going to test choice 3 though, because plugging in 2 numbers is not really enough. So I'm going to plug in the first situation. So 150 times 0.85 to the 0 minus 1 is 150 times 0.85 to the negative 1, and I need the calculator for that second entry, so I could just edit this entry to the power of negative 1, and that's equal to 176.5, which is not even close to 150. So choice 3 is definitely not the answer. Choice 1 is the answer. Now, this is just how to do it on paper, but look, I just want to establish for you real quick that you can definitely get this data on the calculator. You can let the calculator evaluate it for you on its own. You don't have to plug in all the numbers every time. So 0.85 to the power of M, or X in this case. I'm going to go to the table set. Table set auto for both independent auto and dependent. Table start could be any number. Let's say 0. And delta table is 1 as usual, and I go to the table and I scroll. For time 0, choice 1 is 150. Time 2, choice 1 is 108.38. Matches very well. Time 4, 78.301, very close. Choice 6, time 6, 56.572, which technically rounds to 57, but that's just the nature of real life data versus a model, that sometimes you get anomalies and the data doesn't fit perfectly. Time 840.874, which rounds to 41. So choice 1 is definitely the answer. Okay, so here's a similar problem. The table below, I'm sorry, let me erase. The table below shows the temperature T of M of a cup of hot chocolate that is allowed to chill over several minutes M. This is the same data as before, time M, temperature T of M. I look at the data very quickly, 02468, and 150 down to 41. This data fits the equation T of M equals 150 times 0.85 to the M. So they're giving us the model here. Now, which statement is true about the temperature of the hot chocolate? So we're going to go through these one at a time and try to evaluate them as we go. The hot chocolate will stop cooling once it reaches room temperature, 70 degrees Fahrenheit. This is there to see, hey, are you applying your own world situation to this? Knowing room temperature is 70 degrees Fahrenheit, when we drink coffee normally in a room temperature room, but if we look at the data, the data drops way below 70. This is not a room temperature situation. So that's not it. And in fact, this model also does not match that situation. So number 2, the hot chocolate temperature will become negative after 176.5 minutes. Well, we can actually do that here. I'm going to change the table set from auto and asks to for the independent to ask. Okay, so I get to plug in the numbers as I choose. So let's see, 176.5. I get 5 times 10 to the negative 11th. The exponent is negative. That doesn't mean the number is negative. 5 times 10 to the negative 11th is positive. How about 177? It's around the same thing. How about 180? It's 3 times 10 to the negative 11th. That's 0.0. So 10 zeros followed by a 3. How about 200? 1 times 10 to the negative 12th. That's still a positive number, so that's definitely not the answer. Okay. Now the hot chocolate's initial temperature was 127.5. In fact, the initial temperature was 150. So it was not. The reason this number is here, this is the temperature. This is for students who think the initial temperature at time 1. This is temp at time m equals 1. So it's not 127.5. M equals 1 is not the start time. The initial time is m equals 0. M equals 0 is the initial start time. Okay, so T of 0 equals 150. So that's not the answer. So let's see number 4. The rate at which the hot chocolate cools decreases over time. 150, 108. This is a change of negative 42. This from 108 to 78. That's a change of negative 30. So that's a smaller change from 78 to 56. 78 to 58 is 20, so negative 20, and then 2 more is negative 22. From 56 to 41, that's a 15 change, negative 15. Okay, so that's definitely a reducing rate of change. And if we graph this, we should also find that the graph flattens out over time. So I'm going to graph it from x0 to x max from time 0 to time 10. I'm not going to do negative times because, after all, negative times are not physically real in this situation. We started at time 0. So I'm going to graph this zoom fit. So it's going to graph more of the data for me. And I should see if the hot chocolate rate of cooling decreases over time, that the function should flatten out slightly. And in fact, the function does flatten out slightly over time. If I change the window from 0 to 10 to 0 to, let's say, to 20, and I do zoom fit, zoom fit was okay. So zoom fit was 0. we should see it flattening out, and in fact that allows us to see more clearly that the function does flatten out over time. So in fact the answer is choice number 4. All right, look, I know you could do it. Keep working at it. Thanks for watching the video, and stay tuned for the next video starting right now.